All right, AP Calc, we're going to move on into section 5.2 now, and if this section was a Shakespearean play, it would probably be best described as Much Ado About Nothing. Well, that's not entirely true. There's actually a really important concept that gets introduced here in 5.2. In fact, the main concept we're going to be talking about in the second semester, which is, as the title would suggest, the definite integral. So, for those of you who saw that last year, you're going to remember that an integral is this little symbol, that was terribly drawn, is this little symbol that looks something like that, and we are going to talk right now about where that symbol came from and what it means and how it was developed. But truth be told, what we're going to do at the very beginning on this big long slide that I'm working on right now is one of these things that's kind of cool, and I think conceptually it explains what's going on here pretty well, but truthfully, and I need to remind myself this right now, you guys don't get as big a kick out of this as I probably do. So this is one of those sections where you probably could skip through or maybe fast forward a little or listen on fast speed and get the gist of what's going on here. So if we take a look at what's happening in this big messy diagram, this might look a little bit similar to you guys, albeit a little strange, to what we did back in section 5.1. We're dealing with some random curve here, which I'm just calling y is equal to f of x, and you'll notice it is just, in fact, a random curve. I wasn't trying to model any particular function that you may or may not know. And what we've done now is we've taken this whole curve right here, and we've created one large interval that starts over here on the left at what we call our a value, and then it ends over here on the right at what we call our b value. And if we talk about notations, everybody, let's go back to some things that we talked about in section 5.1. This a value on the left can also go by the name x naught or x sub 0. And this b value over here on the right also is sometimes called x sub n. And what we're trying to do here, guys, and I thought I would give you the condensed version rather than completely start from scratch like on this slide right here. The name of the game here is to still try to approximate the area underneath that curve by cutting it up into rectangles. So the very first thing that I did here, guys, I just said I wasn't going to do this, and here I go. The very first thing we're doing here is we're cutting this thing up. We are partitioning this overall interval into subintervals. So you'll notice, guys, the next thing I did was in black. I made this value right here called x1, this one next to it called x2, and I want you to notice right then, I paid no attention at all to my spacing. I'm not worried about getting even or regular subintervals here. It looks like I've made this first gap from x0 to x1 larger than the second gap here from x1 to x2. In fact, you'll notice that's what we used this notation for right here, guys. Delta x sub 1 is the change in x values in your first subinterval from x0 to x1. This one right next to it from here to here, that amount would be delta x sub 2, and so on and so forth. I'll come back to the c's here in just a little bit later on, okay? All right, so let's see what's going on here. Now, you'll notice then, we kind of got bored and we did the old ellipsis right here, meaning there could be more stuff going on right here, but we really don't care. Then what I did is I worked on this odd subinterval here in the middle that ended with a particular x value that we're just calling x sub k. So dumb ways to look at it, guys. X sub 1 is the first x value. X sub 2 is the second x value. X sub k, this is weird, is the kth x value in your subinterval here. And the one right before that, we're going to call x sub k minus 1. Now, looking at some of the notations that we've used before, like for the delta x's, that means that this span across right here, guys, that is going to be delta x sub, and if you look at the other ones, that's going to be delta x sub k. And so on and so forth. And then I did another ellipsis right here. There could be more, don't really know. And now we drew the last rectangle. We know that it ends at x sub n, so the one immediately before that needs to be x sub n minus 1. And again, this span across, that's going to be tough to write in there, is going to be delta x sub n. Okay, so all of those red horizontals represent the width of each one. Now, here's where things get weird. We spent a lot of time in 5.1 talking about left endpoint rectangles, right endpoint rectangles, midpoint rectangles, and trapezoids. For our purposes here today, we don't care which of those that we use. There's a reason why, and you'll see here pretty soon. So if you're looking at these green values that I've called C1, C2, and so on and so forth, and you're wondering how I chose those, don't think too hard. They are completely at random. So this C1 value right here is just somewhere in between x0 and x1. Doesn't really matter where. So what did I do? From C1, I went up until I hit the curve right here and then used that height to make my rectangle like that. Then I chose another random x value in the second subinterval, C sub 2. And again, from that random spot, not a left endpoint, not a right endpoint, not a midpoint, just anywhere. I went up to the top of the curve from there and used that height to complete my second rectangle. Skip a few. I went now to the kth interval and chose this random value right here that we called C sub k. Went up to the curve itself, and there was the height of my kth rectangle. Skipped a few more, went to the nth rectangle, chose a random x value right here called C sub n, went up to the curve itself, a little low on that one, and that then gave me the height of my nth rectangle. So, what's important for you guys to understand, if we were live in class, I would ask you this question: how many rectangles did we just draw underneath that curve? A lot of people want to look at this and say 4. You're ignoring the important idea here that there could be more rectangles in between where we drew those ellipses. Ellipses? Whatever. The point there is, everybody, we have now drawn n rectangles right here. Now, n, the number of rectangles, is going to change a little bit from problem to problem, but okay, that's how many we've drawn. So the goal now becomes, how can we approximate the area underneath that curve by using all of these rectangles? So we're going to walk through this in kind of an interesting mathematical way, and we'll see what all of this looks like and where it shakes out. There's something cool coming at the end of this, I promise. So what we're going to do now, very simply, guys, we're just going to take the area of each one of these n rectangles and add them all together. That's pretty simple. So here we go, guys. I'm going to slide this up a little bit, and here we go. So what's happening? Here, this first little red bracket that I've drawn right here, that represents the area of rectangle number 1 right over here. Take a look, guys. The area of every rectangle is its base times its height. So for the first rectangle, the base right here, well, that's delta x sub 1 above it. So there's your base. And the height of that rectangle comes from evaluating this function at this random x value here, C1. So C1 is the x value. F of C1 is the y value that happens at that spot. So we are multiplying our base times our height, and delta x1 times f of C1, that is the area of rectangle number 1. We move on then. Rectangle number 2 has a base of delta x sub 2 and a height, evaluated right here, of f of c sub 2. So that is the area of rectangle 2. Now I did a plus, then a dot, 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 because there's more coming, and now we move on to the kth rectangle. This is a little bit weird now, guys. And the kth rectangle, here we go, has a width or a base of delta x sub k, that was this amount right here, and a height evaluated there at c sub k. Now, guys, this is not my notation. I stole this out of the old book. So this, if that makes you laugh, f of c sub k, I didn't make it up. But anyway, that's the height of your kth rectangle. So this expression right here, or that term I should say, is the area, no, Mr. Fontana, not of the third rectangle, but of the kth rectangle. Then there's a dot, 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 and then we wrap it all up now with the area of the nth rectangle, the last one. And again, its base right here is the delta x sub n, and its height is f of c sub n. So that right there is the area of the nth rectangle. So it's not very elegant. This is really just brute force. But what we have here is the area of n different rectangles, and they're all being added together. And that gets you a so-so approximation for the area underneath that curve. Are we interested in so-so approximations? Well, it's a starting point, it's a jumping off point, but we'd like to make that better. Okay, so that's what we're going to try to do here. But before we do just that, we're going to start to think about if there isn't a nicer way of expressing this mess that we just came up with right here. Now again, don't look at it as 4 terms, look at it as n terms. And you'll notice every one of those n terms, the 4 that we wrote out, they all kind of follow the same pattern. It's delta x sub some number multiplied by f of c sub whatever that first number was. And when they all do the same thing, and we're adding together a whole bunch of terms that follow the same rules, this is where an old friend of yours, just kidding, probably not a friend, called sigma notation can make your life just a little bit easier in terms of notation. So let's take a look at where this next line in the exercise here comes from. So again, we're still trying to come up with an approximate area. And here's what we did. We now used, and I don't draw a very good sigma, you guys. I'm kind of embarrassed by it. Yours might be better than mine. But we drew this Greek letter sigma right here, which, let's be clear, is not the Greek E, everybody. That's epsilon. Sigma is the Greek letter S. That's going to become important here in about 5 minutes. So sigma means summation. So we are going to evaluate here the expression f of c sub k multiplied by delta x sub k. You'll notice, everybody, that is exactly the notation that we used right here for the kth rectangle. Because what is important, everybody, about the kth rectangle here? Well, the first rectangle is the first one. The nth rectangle is the last one. But the kth rectangle can represent any number here that we want. And if you remember what you learned about sigma notation, everybody, this number down here on the bottom tells you where to begin. We start this whole process by letting k equal 1. So you'll notice here, everybody, our first rectangle was delta x sub 1, so that was actually right here, multiplied by f of c sub 1. So if you put this 1 in for that k and that k, that gets you this very first term right here, which is the first one we should be evaluating and then adding to our total. What do we do after that? After you've let k equal 1, now you increase k by 1 integer each time. So next you'd put in a 2, and the area of the second rectangle would be f of c sub 2 multiplied by delta x sub 2, and that would get you this expression right over here. And you would keep going on and on and on until your k value reaches this number right here. And you do use this number, everybody. You just don't go any further after that. So the last value for k we would put in would be n. And our last rectangle's area then would be found by multiplying f of c sub n multiplied by delta x sub n. So what we have on this second line right over here, guys, in fact, you know what, we'll call that line 1, and oops, no, we'll call that line 1 in case I need to reference that again. This will be line 2. So it probably doesn't look this way to you guys, but lines 1 and 2 right here are identical. They're giving us exactly the same information. I would just say that what we've drawn here first in line number 1 was probably simpler to understand, but more complicated to write out. And then inversely here in line number 2, anytime you throw a sigma in there, I think pretty clearly it's harder to understand, at least at first, but I think you guys can see that this second line right over here was a much more efficient way of writing what we had done up above it here in line number 1. Okay, so that's where we are right now. And I need everybody to understand that lines 1 and 2 right here are really giving us the exact same information. And what did I say that was a moment ago? A so-so approximation for the area underneath this curve. But obviously you knew where this was going. We are not just interested in a so-so approximation. What we want is to make this so-so approximation better so that it's less so-so and more actually decent. So how are we going to do that? How can we take this model, this plan that we came up with right up here at the beginning, and how can we improve it? Well, I think we saw this, everybody, in our 5.1 video and our notes and our homework. The more rectangles that you draw, usually then, the better your approximation for the area underneath that curve is. So we want to go ahead and we want to take this expression or this formula right here for the area underneath a curve, and we want to try to improve upon it by increasing the number, whoops, that was odd, by increasing the number of rectangles, n, that we're going to draw underneath. So think about that for just a second. I asked you guys to look at this diagram and say, how many rectangles are there? And don't say 4, there's n. But okay, let's be finite about it. If there were 4 rectangles, that was it. Is that a good approximation? Not really. So what would be better than 4? I don't know. 7 rectangles would be better than 4. That would get us a closer approximation. But of course, if you're going to do 7, why not do 8? Because 8's better than 7. And then why not do 10? Because 10's better than 8. Well, obviously, okay, the more rectangles we have, the better, but it also gets more tedious to evaluate. That's kind of the trade-off right here. But let's see what we can do. Truly, guys, the ideal number of rectangles we would be dealing with would be a big value of n. And even though this might seem a little bit unrealistic, ask yourself, what would be the ideal number of rectangles? Not 10, not 100, not 1,000 or 1,000,000, but an infinite number of rectangles would get us a really good approximation for the area underneath that curve. And so, ladies and gentlemen, we're going to move on to what I'm going to call line 3 here, and I want you to notice a big change. We are now saying that this formula, which was an approximation for the area, will actually get us the exact area underneath the curve if we take this exact same expression right over here, there, and we apply one little mathematical trick out in front of it, and that would be, everybody, a limit as n approaches infinity. Let's not forget now, n is the number of rectangles. So I want you guys to think about what it is that we're saying right here. A limit as n approaches infinity. Obviously, we can't let n equal infinity because we'd be here all day coming up with the areas of all of our rectangles. But as we learned from some previous chapters there, if we let n approach infinity, meaning if we figure out what happens when n starts small and then gets bigger and bigger and bigger and bigger, if we can see a pattern, we can answer this question then to what is likely to happen if n actually were infinity. So this jump here, guys, from step 2 to step 3, this is really the big conceptual change on this slide right here, even though there's one more line to come. This is how you take an approximation for the area underneath a curve and you turn it into an exact answer of something that heretofore we didn't really know how to do. So this line right here, guys, in step 3, this works. The problem is it's tedious. You've got to sit here and do this whole process multiple times for multiple different values of n, increasing without bound, and hope that you're going to see a pattern in the result that's going to be developed right here. So eventually, there's going to be a change, not just conceptually, but a change in the way that we actually compute this. But we're ahead of ourselves just a little bit. The last line I have to show you guys on this slide right here, everybody, is not a conceptual change, but a notational change. And if you're not familiar really with the word notation, it simply means a way of writing something. So what happened is that over the course of mathematical history here, people realized that just writing this expression that we have right here on line 3 got tedious, and they looked for a way to kind of tighten up the process a little bit. Okay, and I apologize for showing this to you all at once. If we were live, I'd draw this out a little bit more, but here's what happens. This line right here in number 3, this line here, is now going to change, everybody, into, drum roll please, this line or this expression right over here. So let's see what in the world is going on in what I'm about to call line 4. What has changed, everybody? I kind of want to work this from right to left. The delta x sub k now got replaced with something called dx. And let me talk for just a second about something you may have noticed this year and maybe you haven't. Delta x, everybody, delta is a Greek letter that eventually, as a convention, got replaced, not the Greek D, but it got replaced by the Roman D. And just in case you guys aren't familiar, the alphabet that we use today in English is pretty much still the same thing as the Roman alphabet. That's part of the reason that one of the most basic fonts on your computers these days is Times New Roman. All right, so the delta x sub k now got replaced by dx at the end. The f of c sub k, which was the height of your kth rectangle, now just generically became called f of x. And now, here's the really fun part, guys. Let me switch back to purple right here. This big mess right out here, the limit as n approaches 0 of the summation, guys. So basically, the infinite sum, okay, the limit as n approaches infinity of the summation from k equals 1 to n got replaced by this nice, efficient little symbol right over here, the definite integral from a to b. And just in case this is lost on anybody and you haven't seen it figured out just yet, I need you guys to realize what kind of cool thing, no, I want to do this, just happened right here. And the kind of cool thing is that letters changed over time and that we started with this letter right here, guys, the Greek letter sigma, which was the Greek S, which now got replaced by the definite integral sign, which looks a little bit like the Roman letter S. That is not a coincidence, everybody. The Greek sigma, which is the Greek S, then got changed to the Roman S. So just like Greek civilization died out and the Romans kind of took it over and then didn't really come up with any of their own ideas. They just stole all the Greek ones and renamed them, right? Mythology and planets and all that stuff, okay? Kind of the same thing happened in Europe many, many, many hundreds, if not thousands of years later with mathematical notation. Somebody said, all right, look, I can do this with Greek notation, but maybe it's a little bit faster right here if I just change it all to Roman notation. So kind of the joke of all this, everybody, math people laugh about sometimes, is that if you were to show this symbol right here to an Algebra 1 kid and say, what is it? They might look at it and say, it's an S. And a pre-calculus student would laugh at them and say, you idiot, it's not an S, it's an integral sign. And of course, the joke there is that hopefully we now get that a calculus student is going to look at this and realize, oh, dang, that Algebra 1 kid was kind of right. The integral symbol is a funky looking S that stands for an infinite sum. So let's tie all this off with a bow, everybody. So what I now want to discuss here real quick, let me switch my pen back to where it was, is then kind of the breakdown, the anatomy of a definite integral. So this quantity right over here, this integral from a to b, that's our infinite sum. So right here, guys, the symbol itself is just called the integral sign. The a and the b, oh boy, let's go way back. I haven't talked about those in like an hour. The a and the b represent the left endpoint, the left endpoint of this entire interval where we began, and b is the right endpoint of the entire interval where we ended this whole thing. So the a and the b right there, everybody, are called the limits of integration. The lower limit is called A and the upper limit is called B. This quantity right here, the function, and again, let's go all the way back to the original graph, y equals f of x, you guys, that was the curve itself. Okay, so that f of x right there, the function we are evaluating to get the heights of our rectangle, that is called the integrand. That's a word we need to know well. And then this dx at the very end, which frankly, most of you guys probably think right now can be ignored, but is going to be, it's incredibly important conceptually right now. It becomes important practically later on. That one is called the variable of integration. And I do just want to make one little note right here. You will notice, everybody, that's a dot. That's multiplication. Now, you probably never wrote that last year in pre-calculus if you saw integrals at all, and that's okay. Most people don't. But I talk about it right here, and I'll talk about it later on in the chapter as well, as a way of reminding you that what we are really doing right here is we're finding the area of one rectangle. F of x, the integrand, is the height of that rectangle. Dx, the variable of integration, represents the width of that rectangle. And as you may have figured out, guys, as your number of rectangles approaches infinity, as it gets bigger and bigger, the width of each rectangle goes the opposite direction. It actually approaches 0. So that is a huge mess that I have made on this slide right here, and I wish on my iPad I had a way of shrinking all of that down so you could see all of it at once, but unfortunately I don't think that I do, or at least I don't know how to do it. Anyway, so, hot dog, pinch and zoom actually works just like everything else for the last 100 years, or at least it pretty much works. Who knew? Learned something new. All right, guys, so that's kind of what we've learned right here on this slide. Now, most of what we just talked about, let me be clear once again, was a conceptual exercise in understanding where this fourth line right down here on the bottom comes from. And everything we're going to do from here on out deals with explaining how the definite integral is actually used to evaluate some of these problems. I'm going to go ahead and cut this video off right now, and then I'll pick up in just a moment then with part 2.